This section is, for the most part, is review of exponential functions and natural logarithmic function. In the first box, you're looking at the derivative of e to the x and integral of e to the x that you already used. The second box is the inverse property that basically tells you that e and ln are inverse function and it's going to cancel each other. The third box has an interesting property that in many calculus books you will see the definition of ln x as an integral from 1 to the x of 1 of t dt. And look how interestingly that property matches the actual value of ln of 1 equals 0. If we're going to set the integral from 1 to 1 of 1 over t dt, this integral is also 0, just by using properties of integrals. Derivative of ln x, you've seen before, is 1 over x. Integral of 1 over x, doesn't matter in which form it's written, at the bottom of the page, it's always ln of x. And the middle line is 3 laws of logarithmic functions that written for ln that you've seen before. The second page starts from the reminder of the change of base formula, that any log with any base b could be written as the ratio of ln x over ln b. And then the next one is the reminder of the derivative of log of base b. Realize that there are 2 ways you can approach this derivative. You can always rewrite the log as a ratio of ln x over ln b, or you can simply memorize and use the formula. So let's use this formula and let's look at the next 3 examples. First of all, every time when you're looking at the logarithmic function, we're going to try to simplify it. And in this case, we're going to use the power rule. So 10 times 0.4 is going to be 4 log, I believe it's a common logarithm, right, of x. And now we're ready to find the derivative. So h prime of x is going to be equal, 4 stays outside. I'm using the formula, so it's 1 over x ln of 10. So it's 4 over x ln of 10. The second example, part B, again, we're just going to be using the formula. I don't think we can simplify. So f prime of x, in this case, is going to be 1 over secant x ln of the base, which is 4, times, we're applying chain rule, derivative of secant is secant x tangent x. Simplify your answer and you're ready. The last one looks complicated, so let's see if we can simplify it first. I'm using change of base formula for the numerator, which is ln x over ln of 9, and for the denominator, it's ln x over ln of 3. So simplify that expression, and we're looking at ln of 3 over ln of 9. I don't know what number it is exactly, but it's a number. There is no x. So we know that q prime of x must be 0. The last page is, again, reminder, derivative of exponential function of any base b, which is b to the x ln of b. And then if we're going to rewrite it in integral form, so integral of b to the x ln of b dx is equal to b to the x. And if you're going to factor ln of b and solve for integral of b to the x, we're getting to the next formula. So integral of b to the x dx is b to the x times 1 over ln of b. So let's use this property. Just don't forget the u substitution. So u is negative x, du is negative 1 dx, so we're going to factor the minus out. So we're looking at the negative integral of 3 to the u du, and using the formula, it's going to be negative 3 to the u times 1 over ln of 3. And plugging x back, so it's negative 3 to the negative x over ln of 3. So let's look at the next example, part B. Again, we're looking at complicated integrals, so we need to start from the u substitution. U equals negative x squared. Du is negative 2x dx. So divide, we have negative 1/2 on another side. So negative 1/2 integral 5 to the u du, right? Written this, the same integral written in terms of u. Now we know how to integrate it, so it's negative 1/2 5 to the u times 1 over ln of 5, and plugging u back and simplifying the expression, it's negative, so 5 to the negative x squared over 2 ln of 5. And the last example, integral of log, which really we don't know how to integrate, so let's use change of base formula first. So we're looking at the integral of ln of x over ln of 2 over x. We can factor 1 over ln of 2 out, and then it's an integral of ln of x over x, and I'm sorry, I'm running out of the room, dx at the end. Again, u substitution, you know that ln x must be u. Derivative du is 1 over x dx, perfect match. So we're looking at 1 over ln of 2 integral of u du, which is 1 over ln of 2, 1/2 u squared, and then we need to plug ln x for u. And let's look at the last example. Again, starting from u substitution, u is sine x, it's a composite function. Du is derivative of sine, which is cosine x dx, perfect match. So this integral is actually u to the e du, and we can integrate it. It's u to the e plus 1, 1 over e plus 1, which is 1 over e plus 1, and u was sine x, so sine x e plus 1. The last page is basically two very similar examples, applications of integration of exponential function. So we need to find the area of the region between the graph of y equals x times 2 to the x squared, I believe, and the x-axis on the interval from 0 to 2. Let me sketch the graph. And again, I don't know exactly the graph of x times 2 to the x squared. All I know that on the interval from 0 to 2, it's going to be a positive function. So that's going to be our y on the interval from 0 to 2. So we're looking for the area of that region, and in order to find it, so that area is going to be the integral from 0 to 2 x times 2 to the x squared dx. In order to solve it, we need a u substitution. U is x squared, du is 2x dx, factor 1/2 out. So we're looking at the integral, 1/2 integral of 2 to the u du. And let's change the limits of integration. So when x changes from 0 to 2, u changes from 0 to 4. So this integral is going to be from 0 to 4. And we're looking at 1/2 times 2 to the u over ln of 2 on the interval from 0 to 4. Plug in the top number minus the bottom should give us the answer, right? So 1/2 ln2 we can factor, and then it's 2 to the 4th minus 2 to the 0 that I believe you can evaluate. The last question, part B, is even easier than this one, and it's very similar question, so I think you should be able to finish it. All right, thank you, good luck, do your homework.